So we are very happy to have Florian giving the first talk of the year. And he's coming to us from Carnegie Mellon University. He didn't have to travel too far this time. So maybe in a year or two, we will see you actually at UW. But in any case, he's going to talk about the topological Tverberg problem beyond prime powers.
Okay, thank you very much. Yeah, thanks so much for the introduction and for having me. And I didn't have to fly across the country. That's a big plus. That's true. Yeah, it's great. Although I have to say I'd much rather fly across the country. Maybe we can do that soon. Yeah, the topological Tverberg problem beyond prime powers. Maybe the title doesn't make any sense to you right now, even after seeing the pre-seminar. No worries. I'll try to explain things slowly and in detail, and if I miss something, please interrupt me. Again, I have the chat function open on this other screen over there, so I see if people write in chat, but yeah, you can also unmute yourself. I want to begin with, I call it the prehistory. It's very early history. Birch, 1959, the same Birch of Birch and Swinnerton and Dyer, showed the following theorem. If you have 3 times q points in the plane, then you can partition them into q triples so that the triangles that they span, the q triangles, they all share a common point. So here, I guess we have 9 points in the plane, and you can split them into 3 triangles, and they all surround this red cross. No matter how you distribute these 3 q points, you always get such a partition, such a Birch partition. Okay. You can say this in various ways. For any straight line drawing of the complete graph on 3 q vertices in a plane, there's a point that's surrounded by q pairwise vertex disjoint 3 cycles. Right? That's saying the same thing. You could also say for any linear map from the 3 uniform hypergraph, so the hypergraph on 3 q vertices that has all the triangles, right? If you have a linear map from the vertex set to the plane, then there's a perfect matching of hyperedges that all have a point in common if you represent your hypergraph in the plane. That's another way of saying it, just so you have various ways of thinking about this statement. Notice that statement 2, if you think about the analog of this for q equal to 2, what would that be? Sorry, if you replace the 3 by 2, what would that mean? You have a map from the 2 uniform complete hypergraph on 2 q vertices, so the complete graph on 2 q vertices, to the real line. And then you have an intersection of q edges. That's just called a median, right? It's just, you have q real numbers on this side and q real numbers on this side, and somewhere in the middle is this point that's in the middle of these pairs, q pairs of numbers. That's a median. So this is some kind of generalization of median to higher dimensions. And what do people ask about such statements generally? Well, if it's a statement about a linear drawing of the complete graph in the plane, so what about nonlinear drawings? What if you have just any drawing of the complete graph on 3 q vertices in the plane? Do you still have q 3 cycles that surround a common point? What about higher dimensions? What about nonlinear drawings in higher dimensions? So that's what I want to talk about today. Actually, in higher dimensions, yes, that's true. You can even save a few points if you like. So here's Tverberg's theorem from 1966. Any q minus 1 times d plus 1 points in Rd can be partitioned into q sets whose convex hulls all share a common point. Right? If you plug in d equal to 2, the planar case of this, then you get that any 3q minus 2 points can be partitioned into q sets whose convex hulls all share a common point, which is a slightly stronger statement than this theorem of Birch that I just showed. The story that goes with this is, so Tverberg proved this as a graduate student. He's still around, and he visited Brian Birch, right, in Manchester, trying to prove, because Birch conjectured this, after proving the planar case, Birch conjectured this higher dimensional version of his theorem. Tverberg visited him in Manchester and didn't make much progress, but then on the last night in Manchester in the hotel, the heating just went broke or something, and it was really cold, so he had to stay up all night. And what does a grad student of mathematics do if they have to stay up all night? They prove this theorem. So that's the story that goes with it. I guess I should show you some pictures. This is what, 7 points in a plane, meaning we should be able to partition them into 3 sets whose convex hulls all share a common point. Here they are, 2 edges in a triangle in this case. Here's another picture that I got from a survey by Imre Baran and Pablo Soberón. A bunch of points in a plane, I believe 10, right? And we can partition them into 4 sets whose convex hulls all share a common point. These 2 edges and 2 triangles. Okay. And we wanted to ask this question, what about non-linear drawings? What about non-linear versions? Right, so this goes back to Imre Baran, who asked Tverberg in a 1976 letter whether there's a continuous version, continuous generalization of his theorem. Where instead of convex hulls, which is a linear thing, you now have continuous images of faces of a simplex. Also, I believe a precise statement is coming up, but here's the image that you might have in mind, right? So there's a straight line drawing of a tetrahedron, 2 disjoint faces that intersect, but even in this non-straight line drawing of a tetrahedron, there are still 2 vertex disjoint faces that overlap. Now, so what is the concrete version here? You can state Tverberg's theorem in the following way. If you have a linear map from the q-1 times d+1 dimensional simplex, which has q-1 times d+1 plus 1 vertices, and you have a linear map to Rd, then such a linear map must identify points from q pairwise disjoint faces. Yeah, so in the pre-seminar just now, if you happen to be there, we discussed the case q equal to 2 of this and its topological analog, right? That's what Barn asked. Is this still true if you replace linear map by continuous map? So again, here are 2 representative pictures of this. One is a linear map from a tetrahedron to a plane, and one is a continuous map from a tetrahedron to the plane. Yeah, so that's known as a topological Tverberg conjecture. That the statement in linear algebra actually more generally is a statement in topology. It just follows from, you can't avoid this Q4 point. Maybe you want to think about it as starting with a linear map, which by Tverberg's theorem has a Q4 point. And now the question is, can you somehow dig out this Q4 point? Can you pull back faces from this Q4 point without introducing new Q4 points until you don't have Q4 points anymore? Before really going into this, maybe I should say a little bit about why would you care? Why is this interesting? Why did people get interested in this at all? Well, the first slide is the usual thing, because it is. Don't you think it's interesting to know whether this statement is a statement in linear algebra or a statement in topology? Right? That seems like a natural question. Is it a rigid statement in geometry, in discrete convex geometry, or is it a flexible statement that just talks about continuous maps and connectivity? And this is interesting to study because sometimes you get surprises. Sometimes you get a rigid version that doesn't have a flexible analog, continuous analog. And also, studying this is a natural generalization of non-embeddability, right? So the characterization of non-planar graphs, for example, that falls into the realm of these theorems. If that's not convincing to you, if you say, okay, that's fine, you can study this, but I can't be bothered to be interested in this, it's also, the reason that people are interested in this question is also because it's a testing ground for methods. It's the canary in the coal mine for topological methods in combinatorics, right? The methods that we use for this problem, you can use the same methods or very similar methods for all kinds of problems, such as fair division problems, necklace splitting, chromatic numbers of hypergraphs, measure partitions by fans, the square peg problem, whether does any closed simple curve in the plane inscribe a square, have 4 points that form a square. That's still an open problem, but the progress we have on this uses methods that are very similar to methods developed for this problem. Yeah, and more problems. Yeah, so there are all kinds of ways where this shows up. So those are some of the reasons why you could perhaps care. Now, if we want a topological version of this, then we will have to do some topology at least. The case Q equal to 2, again, if you saw the pre-seminar, we just stumbled through a proof sketch of this. So if you have a continuous map from the D+1 simplex to RD, then it's actually true. There are two disjoint faces of the simplex, vertex disjoint faces of the simplex, whose images under F overlap. And this was proven by Baran and by Motzi. I guess I even have a slide that again reminds you roughly of what the proof was. So if you have a map from the D+1 simplex to RD, simply define a map on the boundary of the D+2 dimensional cross polytope, but now to RD+1. Fix two opposite facets. On both facets, use your map little f. And in the last component, in the last coordinate, use 1 up here and -1 down here, and then shoot rays along the annulus between them and extend along those rays in a linear fashion. Use Bose-Coulomb. Right? You get a map from a D+1 sphere to RD+1 with f of -x is negative f of x for all x. Bose-Coulomb precisely says that any such map must have a 0, and you check that this actually implies that f identifies 2 points from opposite faces, from disjoint faces. They're disjoint because no facet of the cross polytope contains integral points. I want to present another way to think about this proof just because it'll be convenient later on, which is you can think about it in this way. Given a map from the D+1 simplex to RD, assign the label 1 or 2 to every vertex of the simplex. And now check whether the face spanned by the vertices with label 1 intersects the face spanned by the vertices with label 2. Okay? And these labelings, they're naturally parameterized by the facets of the cross polytope. Any facet of the cross polytope gives you a 1-2 labeling. Any 1-2 labeling gives you a facet of the cross polytope. And by check whether they intersect, in some sense, you just use the Bose-Coulomb theorem to say, yes, on some facet, for some 1-2 labeling, they must intersect. That's another way of thinking about what's going on here. So how then would you approach the case Q equal to 3 or higher Q, more faces that intersect? What do you need if you want to generalize this? Well, Bose-Coulomb is not good enough anymore. You need a generalized Bose-Coulomb theorem that hopefully someone has proven for you, right? That guarantees that certain symmetric maps have zeros. And instead of labelings with 1 and 2, you now label your vertices with 1, 2, up to Q. And then you have a face spanned by the 1s, a face spanned by the 2s, and so on, the face spanned by all the Q labels. And you check whether they all overlap in a common point. And this, hopefully, your generalized Bose-Coulomb theorem is true for this labeling complex. Okay, the generalized Bose-Coulomb theorem, yes, it is true. Someone has proved this for you. Dolt in this case. If G is a group that acts on R to the D, such that the action away from the origin is free, so every group element moves every vector in RD without 0, and X is a homologically and homotopically D-1 connected simplicial complex with an action of G, then any G equivariant map, any map that commutes with the symmetries given by G, must have a 0. Notice if you plug in G equal to Z mod 2, there's just one involution, and X equal to SD, then this is the Bose-Coulomb theorem. Okay, and what we want to do is we want to use this for G is Z mod Q, because instead of 2 faces, we now have q faces. And how does z mod q act on rq minus 1 in this case? Think of the simplex centered at 0 in rq minus 1, and z mod q just shifts the vertices one by one around. Right? And now, well, there was this word prime powers in my title. How do these number theoretic conditions arise in this? Notice this action that shifts around, that's only free if q is a prime. Meaning, if q is 3, right, this action is on R2, and you have a triangle centered at the origin, and you rotate the triangle by the 3rd turn, and that's a free action, only the origin is fixed. But if q is 4, which happens to not be a prime, you have a tetrahedron centered at the origin, and if you send the vertices of the tetrahedron around in a cyclic fashion, what happens? Well, if you go 1 click, everything is fine, but if you go 2 clicks, this happens, right? You just swap, you just interchange the vertices of 2 edges, which fixes this entire line in the tetrahedron. So you don't have a free action. Now that's how number theoretic conditions come up in this problem. The other ingredient we needed is the Q labeling complex. Yeah, what's the complex? Where the facets are now in bijection with labelings by 1 through Q. Well, it's complex that you can denote by in this way here. That's how you could denote it. What do I mean by it? I mean, you have Q copies of the vertex set. So vertices are called 1 through n plus 1, say, times 1 through Q. And what are the faces of this complex? Well, a set of vertices is a face if you never contain 2 copies of the same vertex, right? So n plus 1 and Q, you can think of this as, I don't know, maybe what you have in your mind is, something like this maybe, right? Where this is n plus 1 vertices and this is Q vertices. And you're never allowed to take 2 copies of the same vertex. So never take 2 vertices in the same row. You can do this, this, this. That's a perfectly valid face of this complex. Just never take 2 vertices in the same row. If you check that this complex is actually n minus 1 connected, you're done, right? Then you have this theorem of Baran, Schlossmann, and Jeeves that for Q prime, because we need the action to be free, any continuous map from the Q minus 1 times D plus 1 simplex to RD identifies points from Q pairwise disjoint faces. Now, so you have this continuous analog of Tverberg's theorem, but only if Q is a prime. You have to pay the price for the action being free. And of course, you want to know, is this something that is actually needed, or is this a proof artifact? Well, actually, you can push this a little further. You can generalize this theorem of Dold. There's even more general Borsuk-Ulam type statement. If Q is a power of a prime, then instead of the group Z mod Q, you use Z mod that prime to the K, which is an elementary abelian group. And for elementary abelian groups, there's such Borsuk-Ulam type statements, even if the action is not free, as long as the action doesn't have fixed points. So the difference is, in a free action, every group element moves every point, right? But in a fixed point free action, there is a group element, right? So no point in your space is fixed by every single group element. And then once you know that, you can get this result of Uzaydin and independently Volovikov. For Q a power of a prime, this continuous statement, this continuous generalization of Tverberg's theorem is still true. So if you draw a very large simplex in R to the D, then, and by very large, I mean precisely this number, Q minus 1 times D plus 1, then you can find Q pairwise disjoint faces whose F images overlap, provided that Q is a power of a prime. Funnily enough, this topological way of showing this fails completely beyond prime powers. So here's a recent result of Avakumov, Karaseov, and Skopenkov. If Q is not a prime power and X is a complex with a free action by the symmetric group, say, so even a larger group than what we've been working with, then there is an equivariant map, one that commutes with symmetries from x to rq minus 1 squared without a 0. Yeah, so notice there is no quantitative bound here. Yeah, so if you want to say, okay, maybe topological Tverberg, I can't prove it for this number q minus 1 d plus 1, but what if I take a very large number? I take a very large simplex. I take a simplex on, I don't know, q squared times d plus 1 vertices, and then I go through the same proof. Your proof still fails if q is not a power of a prime, because the topological machinery doesn't work in any way beyond prime powers. What's even worse is not only does the topology, this proof method, not work beyond prime powers, it cannot work beyond prime powers because this continuous analog of Tverberg's theorem is simply wrong beyond prime powers. Yeah, so if q is not a prime power, then you can find counterexamples. And this somehow, so that's one of these surprises that I perhaps mentioned in the beginning. So think about how strange that is. Tverberg's theorem is a result in linear algebra if and only if q has at least 2 distinct prime divisors, because otherwise it's a result in topology, right? And somehow you can't extend beyond prime powers using these methods. Yeah, so and people have proven all kinds of counterexamples. Not only is it wrong, it's very wrong beyond prime powers. Yeah, so you can, so here this says that you can add any constant, and then if d is large enough, it's still wrong. And more recently, you can even do this, right? So that's almost q times d plus 1 minus a little bit, where it's still wrong. Yeah, so very wrong. Okay, these are all lower bounds. What I actually want to talk about today are upper bounds, which might be surprising because I just told you topological methods fail completely beyond prime powers. Yeah, so for prime powers, we have the tight upper bounds. We know precisely what the number is. Beyond prime powers, we don't know what it is. It's not the same number. And our usual proof methods fail completely. So we need to have new ideas. Certainly, this number is finite, right? If you ask the question, what is the smallest n such that for any continuous map from the n simplex to Rd, I have q pairwise disjoint faces whose f images all overlap, then even if q is not a prime power, that number is still finite. For the simple reason that, you know, if your favorite number is not a prime power, then I just go to the next prime power and I apply the topological Tverberg theorem for this prime power, and then I forget about a bunch of faces, right? And that gives me an upper bound. So the upper bound you get in this way, let's see, what can you do? Well, I should go, here I say, if R is a prime power that's larger or equal to Q, then certainly, you know, for maps from the R minus 1 times D plus 1 simplex, I even get R faces that overlap. So certainly I get Q because Q is less than R. I can save a few more points by saying, in advance, let's agree on R minus Q points, such that the faces that contain those R minus Q points, I will forget about those faces in particular, right? Then you can save R minus Q additional points. So that's, yeah, here I'm saying for D at least 2 and Q with at least 2 distinct prime divisors, there's no better bound that I'm aware of. Yeah, other than this trivial construction of just go to the next prime power and do it for the next prime power. Well, so far, of course, my whole point I'm building up to telling you that Pablo Soberón, my co-author on this, and we can actually prove upper bounds beyond prime powers now. Okay. Notice the following. If Q plus 1 happens to be a prime power, no, maybe Q is not, maybe Q is 6, not a prime power, but Q plus 1, 7 is a prime, so in particular a prime power, then what I just said means that any map from the Q times D plus 1 minus 1 simplex to Rd identifies points from Q pairwise disjoint faces. And this is the number that we saw in Birch's theorem. If D is 2, right, this simplex has 3 times Q vertices. So the natural generalization of Birch's theorem is true if Q or Q plus 1 is a prime power. So if we go back to this original question about drawings of the graph, if you draw a graph on 3 Q vertices in the plane, then there are Q vertex disjoint 3 cycles that all surround a common point, provided that Q or Q plus 1 is a prime power. So your hope could be perhaps Tverberg's theorem is false, the continuous generalization for Q with at least 2 distinct prime divisors. But maybe if you add a few points, Birch's theorem is still true. And that's in fact true. So what we proved is if Q is any integer you like, then any continuous map from the Q times D plus 1 minus 1 simplex to RD identifies points from Q pairwise disjoint faces. This is optimal in the following sense. A generic map does not identify Q plus 1 pairwise disjoint faces. Yeah, so Q is the best you can do here. And these are precisely the bounds that I conjectured previously together with Pablo Blagojevich and Günther Ziegler. So that's a little suspicious that we get precisely this bound that we conjectured earlier, but there are good reasons to believe that that's a correct bound actually. I should maybe wait a little bit. Is a statement of the theorem, does that make sense to us? Or the questions, comments? Seems good. Okay. I want to say a few things about the proof, just because there must be new ideas in the proof. Maybe some of them are useful. First of all, you can prove a special case of this in a much simpler way. Namely, the special case if 2Q plus 1 is a prime. So let's talk about the planar case. If you have a drawing of the graph, of the complete graph on 3Q vertices in the plane, then you can just think of it as a drawing of the complete graph on 6Q vertices in the plane by saying, secretly, I drew every vertex twice, right? So it's a very degenerate drawing of K3, of K6Q in the plane by doubling every vertex. But 6Q is 2Q plus 1 minus 1 times 3. Okay, so what do I want to do? I want to now find 2Q plus 1 pairwise disjoint faces whose images overlap, but maybe they share vertices because I doubled vertices, right? So I have to somehow say, and Q of these do not share vertices. Q of those 2Q plus 1 faces are actually vertex disjoint. And that's something that, there's a theorem of Vucic and Javaljevich that says, it's the following Tverberg type statement. If P is a prime, and you have a map from the usual simplex, the P minus 1 times D plus 1 simplex to RD, then not only does it identify P points from pairwise disjoint faces, but you can even constrain the faces in the following way. Number your vertices, label them 1 through however many vertices there are. Then if vertex 1 is in phase number J, then the next vertex, vertex 2, is in phase J or in phase J plus 1. And then this has nothing to do with all the other vertices, but then there's the next pair. If vertex 3 is in phase J, vertex 4 is in phase J or J plus 1. Mod P, obviously, right? So P plus 1 is 1 again. This is simple to prove because the complex of labelings is a join of circles, right? So what's the labeling complex in this case? Maybe I'll draw here. So if you just look at the first 2 vertices, so this is P, and this is vertex 1, and this is vertex 2. If vertex 1 is in phase 1, then vertex 2 is also allowed to be in phase 1 or in phase 2. If vertex 1 is in phase 2, 2 is in 2 or in 3. And you see where this is going. I just continue this. Zit out here again. That's the circle. And the entire labeling complex is a join of circles, which happens to be a sphere. And so it's homotopically highly connected, and that finishes the proof. So that's, yeah, if you know how these proofs go, then this is quite easy. Here's a nicer picture of this. What are the allowed labelings of vertex 1 and 2 and vertex 3 and 4 and so on? Why does this help? Let's see, why does this help? Maybe I should stay on this slide. This helps because if you double the drawing of your complete graph, you now get 2 Q plus 1 faces that all share a common point, but also with this restriction. So now only retain every other face. Yeah? Retain face 1 and 3 and 5 and 7 and so on. In total, this gives you Q faces. And they have no vertices in common because, well, can they share vertex? If you doubled vertex 1 to vertex 1 and 2, then they never appear, in phase 1 and 3 because of this restriction. They can only appear in phase 1 and 2, only in consecutive phases. So this gives a simple argument that actually this theorem here is true if Q is a prime power, or Q plus 1 is a prime power, or this new reduction if 2Q plus 1 is a prime. And now it's a not very interesting exercise in number theory. What is the smallest number Q that is not a prime power, such that Q plus 1 is not a prime power, and such that 2Q plus 1 is not a prime? I actually had fun on these slides doing this. So here are a bunch of numbers, 2 through 51. Let me strike out every prime power for you. Okay, I hope I got all prime powers. Now let me strike out every number such that the number plus 1 is a prime power. Okay, so for example, 6 now is struck out. Okay, a few survive, but now let me strike out everything such that 2Q plus 1 is a prime. So for example, the smallest number you see here is this 14. But 14 times 2 plus 1 is 29, and 29 is a prime, right? 20 times 2 is 40, plus 1 is 41 is a prime. 43 is a prime, right? So actually the smallest number that's not of this form is 34. So I just proved the theorem in this almost trivial way for you for every number that's at most 33. Okay, so, but that's just, yeah, that's a somewhat silly argument. So what's the key new idea to prove this? So recall, what did we say? To prove this topological Tverberg theorem for Q, let's say a prime or a prime power, what did we do? We label every vertex with one number in 1 through Q, and then ask whether the Q-induced faces by this labeling have a point in common, right? And the key idea now is, so if you present it in this way, then I guess the key idea is almost obvious. Instead of labeling each vertex with a number in 1 through Q, label it with a subset of 1 through P taken from some simplicial complex on the vertex set 1 through P, where P is a large prime. Now, I want to reduce to the prime case. And what do we want to do? We always want to find a subset of Q labels such that no 2 appear at the same vertex. Let me be a little more specific. So to apply Dold's theorem to this new label complex, what do we need? First of all, Dold's theorem only applies to simplicial complexes that are symmetric, that have a free group action. So certainly our simplicial complex should be Z mod P symmetric. And to apply Dold, it should also be homotopically highly connected. Turns out what we will need in the end is it should be P, the large prime, over Q, the number that you gave me, minus some constant connected, no matter how large P is. And to get Q pairwise disjoint faces from it, in the way that we just saw in this silly idea, we need an independent set of size q in our simplicial complex. Okay, so I've reduced this to the question of constructing a very specific simplicial complex. A simplicial complex that is symmetric, highly connected, and has a large independent set. Notice how highly connected, highly homotopically connected, and large independent set, they're at odds with each other. Right? Large independent set means your complex is sparse. Highly connected means your complex is dense. Right? So these two properties, denseness and sparseness, you have to balance them, and hopefully somewhere in the middle there's the correct complex. So here I'm saying specifically what we need. So if you want to prove this theorem that I advertised for a given Q, this topological Tverberg theorem, somewhat relaxed version, find an integer that's much larger than some constant times Q times the dimension, such that P equal to AQ plus 1 is a prime. And then construct this label complex sigma on vertex set 1 through P that is ZP symmetric. You can shift the P vertices in cyclic order and nothing ever changes. That's sufficiently dense to be P over Q minus this constant connected, and sufficiently sparse to have an independent set of size Q. And that's, yeah, so Pablo and I understood about 2 years ago that that's what you need. The problem is this is difficult to construct. Namely, these last two properties, they can only just barely be balanced. No, you can't do better. Sorry, what?
Can you say what the definition of homotopically connected is? Sorry.
Oh, sorry. Yeah, maybe I should say something about this. So a complex is homotopically n-connected if the first n homotopy groups are trivial, or if that's something you feel a little weird about. What I'm saying is it's simply connected. Every loop can be filled in with a disk, and all the homology groups up to rank n are 0. That's what I want. Why is this what we want? Well, if you have your favorite continuous map from the Q times D plus 1 minus 1 dimensional simplex to RD, first of all, I add one dummy vertex that we'll hopefully be able to forget about in the end. And that gives me n plus 1 vertices in total. And now I label each one of them with a face of sigma. Since the n plus 1 fold join of sigma is very highly connected, because joins behave nicely with connectedness. If you have two spaces that are n and m connected, then their join is n plus m plus 2 connected. So you can just compute how connected this weird join is. You use Dold's theorem and you get P faces whose images under F all intersect. But are these P faces pairwise disjoint? Of course not. P is a very large prime. You get many, many billions of faces that intersect, let's say. But you have this constraint that every vertex is contained in a face whose indices form a set of sigma. Right? That was our construction. The dummy vertex cannot obstruct all independent sets of size Q since P is a prime. If it did obstruct, then P would be something times Q. You can easily check. Meaning there are Q pairwise disjoint faces because there's an independent set of size Q in sigma. Right? You just pick the independent set of faces, and in sigma, right, you pick vertices in sigma correspond to faces now. You pick these Q vertices in sigma that are pairwise not joined by edges. That precisely means that the corresponding faces are disjoint. Okay, that's the proof idea. How do you get such a complex? Right? How do you get a complex that balances local sparseness with global connectedness? Your first idea might be, this reminds me of expanders. Right? Expander graphs or expander complexes, they're precisely that. They're locally sparse, but they have a nice connectivity property. But notice that our complex is also supposed to be symmetric. So all of that is out of the window. You know, you can if you like, you can think of this as symmetric expanders in some sense, right? That's what we need. But symmetric expanders are very different from expanders. What's our first attempt to construct this? So what we need is a simplicial complex on vertex set 1 through p that is symmetric. You can shift the p vertices through and you never change anything. And you want large independent sets of size q vertices that don't share any edges. Well, just define the vertices 1 through q to be an independent set, right? And now take the maximal ZP symmetric simplicial complex that does that. So 1 through q are an independent set, so 2 to q plus 1 are also an independent set, and so on. You shift this around. And now any way that you can pick vertices such that they're always pairwise at least q apart in cyclic order, that's a phase. I call those the q stable sets, right? So for example, 1, q plus 1, 2, q plus 2, and so on, that's a phase because any two vertices are at least q apart. That's ZP symmetric. It has large independent sets, but it doesn't work. It's at most p over 2q connected. It's not connected enough. What's the problem? Well, here's an example. If q is 4, so we want a 4 stable set, any two vertices hopefully are 4 apart now in cyclic order, and p is, let's say, 9q plus 1, which is 37, then do we agree that this is a phase? Yeah, so any two numbers in this set are at least 4 apart modulo 37, right? Even 34 plus 4 is precisely 1. So that just barely works, right? But now notice you cannot add any number to it. You can't add 5 in between here, right? Because 5 is too close to 2 to 8. It's only 3 away, right? And for the same reason, you can't add anything here and so on. So this is an isolated phase. This phase certainly shows up in homology. It's not the boundary of anything, right? But it's only 5-dimensional, and that's not connected enough. So that first idea doesn't work. What you could try instead is only take those q stable sets that can be extended to have only the q stable sets that are allowed to be large. So if in our running example, q is 4, p is 37, I no longer want this phase because it cannot be extended to have size 8. If I only retain those phases that can be extended to have size 8, then I can allow a bunch of short gaps, or I can allow one large gap, or any reasonable combination of these two. And now, yeah, that's what it is. You can work, and I think it takes quite a bit of work to show that this complex is actually p over q minus 4 connected. I certainly won't bore you with the proof of this, but the idea is you first break symmetry, right? You first only regard this. So instead of also the last vertex can be adjacent to the first vertex now. First look at those complexes. There it's very easy to show that they're highly connected. And then use some ideas of Nerve-Lemma and Meyer-Vittori sequence and do this a lot to compute the connectivity of this. And it's somewhat technical, but not too bad. And in the end, you get it's p over q minus 4 connected. Why did it take us so long to come up with this and compute this precisely? Because it is precisely this middle ground of balancing the local sparseness with the connectivity. Yeah, so this complex is optimal. If q is an integer, then for any sufficiently large prime p, the maximal size of an independent set in any ZP invariant complex on 1 through p that is highly connected in the sense that it's p over q minus little o of p connected is q. You can't do better than this. So our construction is optimal in this sense. The remark is, why is this theorem true? Does this take a lot of things to prove this theorem? No, if it wasn't true, if you could have an independent set of size q plus 1, then you can prove Tverberg type results that are too good to be true. right? That we know that are false. I don't know, I have a few minutes. Maybe I'll just advertise this a little bit. I said that there's the topology completely breaks down beyond prime powers. Yet in this, with this combinatorial trick that we added here, we were able to prove this topological theorem. So that's weird, right? The equivariant map machinery doesn't work, yet we could prove this theorem. So what kind of result do you get if you just trace back to the topology? There must be some result there. Well, and let me just tell you what it is. So you could think of Dold's theorem in this way. If Q is a prime, then any map from the Q-fold deleted join, this labeling complex that we had earlier, to RD, maps an entire ZQ orbit to one point. All the Q points that are in one ZQ orbit all map to the same point. If you plug in Q equal to 2, this is precisely Bose-Ulam. And this is false if Q is not a prime, no matter how large n is. Even if n is very, very large, it's still false if Q is not a prime. You can project the Q-fold join of a simplex back to the simplex by just collapse the Q copies of a vertex into one vertex. And then the consequence of this result is if Q is a prime and n is large enough, then any map identifies Q points such that their projection under this map is equal. This is still precisely Bose-Ulam. You can check for Q equal to 2. And now for non-primes, what do you get? So if Q is some integer which is not a prime perhaps, and n is slightly larger, then any map from the, now Q plus 1, I shouldn't mark so much, but here, from the Q plus 1 fold join, identifies Q points that still map to the same point. So that's why the topology is weird here, right? If you trace it back to the topology, it's a somewhat unnatural statement. You have a Q plus 1 fold join. You want to say there's a Q plus 1 fold symmetry, but you only get Q points, right? That are the same under this projection map. That's why, so that's the topological statement that's behind all of this, in some sense. Okay, maybe as a last thing, I'll just show you there are future directions. For example, there's this Baron-Lahmann conjecture that is still open. Kind of a colorful Tverberg. If X is a set of Q times D plus 1 points in R to the D, and they're colored by D plus 1 colors of size Q. And so here in the plane, you have 3 red, 3 green, and 3 blue points. Then there's a rainbow partition where you don't use any color twice in any convex hull, whose convex hulls all share a common point. That's known in the plane, and that's known if Q plus 1 is a prime, but it's open in general, and that's something that we're currently trying to get at. And maybe this is a good place to stop. Thank you.
So let's unmute ourselves and thank Florian for such a wonderful talk.
Thanks. Maybe I should stop the share so we can see each other.
Great, but now wait, you're not off the hook yet. Questions. And maybe you will need to start sharing again. So
I can.
You already were asked a lot of questions, but any additional questions?
Sorry, this is not a math question, but I'm just so curious. How did you get yourself in the bottom left of your screen?
I gave this talk in Oberwolfach 2 weeks ago, and that was also the question I got. What you want to do is you want to download a software called OBS, and it lets you mix the video input. Yeah, and my iPad is hooked up to my laptop, and I'm just projecting the iPad on the green screen.
Thank you.
Any more questions, perhaps mathematical ones? Can you show your last slide, actually?
Yeah, let me share this again. Share. Last slide.
So in what cases is it actually known?
It's true in the plane. That was Barn and Laman's original paper. And the continuous generalization is true even for any dimension and if q plus 1 is a prime. And to my knowledge, that's all that's known. So in particular, this simple question, right? So if you want something to figure out if the heating goes off or something, this is still an open question in R3, for example. Right? Even the linear version of this, if q plus 1 is not a prime, is open in R3.
Oh, even the linear version is open.
Even the linear version is open. Which it doesn't really have any reason to be open, I feel like. If, yeah, so q plus 1, a prime that fails if q is 3, for example, then q plus 1 is not a prime. So given 3 times 4, 12 points in R3, partitioned into 4 colors of size 3, is there such a rainbow partition? To my knowledge, that's open. So a statement about 12 points in R3.
Thank you. Any
Thanks.
more questions? Okay, then let's thank Florian again.